Hi, my name is Arpan Kusari. I'm an assistant research scientist at University of Michigan Transportation Research Institute, and I am presenting our work on estimation of robust normals for LiDAR data using graph theoretical approach. This work has been jointly performed with Dr. Wenbo Sun of UMTRI. Our motivation for pursuing this proposed work is that there is a lot of prior work on normal estimation, but it is still an open research problem in case of multiple invalid structures contaminated with noise. LiDAR points can be inherently described as a graph structure where the points can be the nodes and the edges provide constraints between the points. However, there is very little work on utilizing graph structure in LiDAR point clouds, and we hope our work fills the gap in providing the first principle treatment of graph formulation for normal estimation. Normal estimation can be broadly divided into two sets of methods, regression-based and Voronoi-based. In regression-based methods, the most popular is the use of principal component analysis, or PCA, to estimate normals for each point using its neighbors. It has two big disadvantages. It is sensitive to noise and it fails to preserve edges. There has been multiple approaches proposed to take the normal estimation robust to noise by adding weight or changing PCA to least median squares, or LMS. Edge preservation has not been studied in great detail. Two of the approaches either use piecewise planar surfaces or robust M estimators to formulate two independent initialization to arrive at a solution with most support. Voronoi-based methods, on the other hand, estimate the normal vector as a line through a given point to the furthest vertex of a Voronoi cell. It works well in case of ideal point cloud, but breaks down in the presence of noise. In our proposed approach, we start with the PCA normal formulation as detailed in this equation. However, due to noise, we have to add a regularization based on graph Laplacian, which provides some sort of smoothness constraint on the points as detailed in this equation below, where lambda is the hyperparameter. The matrix form of the optimization can then be written as the following equation, where the R and the C denote the row projections and column projections of the normal vectors, and the XCI denote the difference in other points to the given point xi. The choice of the graph Laplacian is an important consideration in our work. We choose the most basic form of proximity graph, K nearest neighbor graph, to represent the sample points. In the KNNG formulation, two vertices are connected if the distances are among the K smallest distances. The adjacency matrix can then be given by an exponential of the distance squared divided by a standard deviation. The Laplacian is given as a combination of the degree graph and the adjacency graph, where the degree graph denotes the number of edges from each node. The optimization detailed in the last step is a constrained convex optimization with equality constraints, which make the whole optimal solution intractable. We choose a projected conjugate gradient descent algorithm to get a numerical solution. The normal is updated in every iteration as a gradient update, where the gradient is represented by the following equation. The updated normal is just then normalized by normalizing each row to its unit vector. Until now, we haven't talked about the preservation of edges. We use weights to correct the estimation bias in boundary points. The formulation is a weight matrix which gets added in the entire optimization equation. There are different kinds of weighting strategies that can be utilized, which are intuitive. The first one is a dot product between normals. The second one is a distance between points, or inverse of distance between points. And the third one is a combination of the dot product and inverse distance. We show the effect of the weighting strategies in the following slides. We first create a simple simulation to understand the effectiveness of our approach. We sample points from 3 mutually perpendicular planar surfaces by adding Gaussian noise corresponding to 4 levels of standard deviation, as shown in these figures, for 30 iterations, and compare the estimation performance for the different weighting strategy. There are 2 sets of plots for 2 different types of noise levels, shown in the left side and right side. In these plots, the left side figures are given for the loss functions given the iterations, and the right side of each figure gives the accuracy for each iteration with respect to each iteration, where the central line gives the mean of 30 iterations and the shaded area represents the 3 sigma standard deviation. The lines on top show the accuracy of the other state-of-the-art method that we use to compare with ours. We see that our methods perform much better than other state-of-the-art methods, and in between our weighting strategies, the combination of dot products and distances provide a very good convergence with high accuracy. For the previous results, the lambda is fixed at 0.01. We can also see the effect of changing lambda where a larger value is faster convergence, as shown in the figure below. We then run our algorithm on the SynPeb dataset, which provides a comprehensive benchmarking dataset for planar estimation. From the tables shown below, we see that our proposed approach outperforms other methods in terms of the correct number of points assigned and the smaller estimation bias. We find that the graph Laplacian avoids excessive segmentation due to smoothness constraints. Our approach provides a natural way for robust normal estimation. The weighted version also takes care of preservation of edges. Our future direction would be to thoroughly explore graph formulations for LiDAR data. Thank you.